Welcome to our podcast on heat of formation. Now, this whole section we've been spending time talking about enthalpy and what it is, and the next video was on Hess's law and how it works. And so we want to just take this one more step and talk about the heat of formation. Now, go ahead and look at that definition. It's kind of wordy, and you'll notice a couple things. You see a little F here, right? That's formation. And you see a little zero there, or it looks like a degree sign. That also has some significance. So if we look at this definition, it talks about the net amount of heat absorbed or released when 1 mole of a compound is formed from its elements in their standard states. Well, what is a standard state, you might ask? First of all, it's when the substances are at 1 atmosphere, which is basically just pressure that we are at sea level here, and 25 degrees Celsius. A little warmer than room temperature, but you can kind of just figure out what is a chemical going to be at just in normal everyday conditions. Now, the standard state is what this little sign is right here. That tells us it's standard state, that degree sign. And then the little delta H sub F, that just means heat of formation. And in fact, when you move on to some other chemistry, maybe some AP chemistry, there's heat of reaction, heat of solution, heat of combustion. There's all sorts of little subscripts written down there. But for right now, we're going to focus on the heat of formation. Okay, so here's a reaction, and what this tells us is that when we take aluminum in the solid state, because that's what aluminum would be, right? Then we take oxygen gas in the solid state, and when we react those two together, we get aluminum oxide. And aluminum oxide at room temperature at 1 atmosphere pressure is at the solid state. And so this is the energy or the heat that's given off. Notice there's a negative sign right there, right? So that means when you form aluminum oxide, 1676 kilojoules is given off. Now, you could add this, kilojoules per mole, because it's a formation of 1 mole, right? But you look at this and you go, whoa, Richardson, did you notice that you did not balance your reaction? And normally that would be a mistake that I've made because you guys have seen me make podcasts before, but it turns out I didn't. I just left it here because I wanted to show you something that we haven't seen yet this year, and I don't want to freak you out. So let's go ahead and balance it. Now I see there's a 2 there, and so I would put a 2 there, and then there's a 3 there, and there's a 2 there. And wait, if you recall how we balance, I would go ahead and put a 3 there and a 2 there, and I would switch this and make this a 4, right? But let's look at our definition. It's the amount of heat when we get 1. There it is right there, 1 mole. Okay, and this is not 1 mole as written like that, right? Now, the important thing to remember is, the heat of enthalpy is one of those things that it's an extrinsic property, right? The more stuff you have, the more heat you have. And so if there was a 2 right here, really I would have to double this number, right? Times it by 2. But there's got to be another way, right? So what we're going to do is we're just going to write this so that we get 1 mole formed, which is not a problem because we can do that. We have the skill. We're going to use a fraction, which is weird. So anyways, I'll go back to 2 aluminums, put 2 right there, and then I need 3 oxygens. Well, if I take 3 halves O2, think about this. 2 times 3 is 6, right? And 2 divided into 6 would give me 3. So there we get it balanced. Now, don't worry about the fraction. Don't let it bother you. The important thing is that we write this out for 1 mole of a compound. So that's the heat of formation. So what I want to do is I want to do that for 2 other compounds just to make sure you have a feel for this, because it turns out that these heats of formation are extremely useful in finding the enthalpy of a reaction, which is what's next. So here we go. Question says, write out the heat of formation at the standard conditions for CH4, which is methane, right? So I'm going to write what's going to make up methane? Well, at the standard state, the element carbon, right? Now, carbon, by the way, is a solid at standard state, okay? And then what else looks like it's hydrogen? So I write hydrogen as H2, right? You guys know that. And hydrogen is a gas at standard state. And that, of course, yields methane, CH4 in the gas phase, and the delta H of formation equals a negative 74.9 kilojoules. Now, it's not balanced, right? You're saying? Well, no problem. Let's balance it. Got a 4 there and a 2 there. I'm just going to put a 2 there. So I've essentially written out that reaction, the heat of formation of methane, along with its the enthalpy value. Okay? Not too bad, right? What I'd like you to do, if you feel confident, pause the video. Try and write the heat of formation for sodium carbonate. See if you can do it. How'd you do? Well, this is what I would do. First of all, again, I've got to find the elements that make up sodium carbonate. So we've got some sodium, right? So sodium, and sodium's a solid, standard conditions. Then I've got some carbon, right? Carbon's a solid, some standard conditions. Then I've got some oxygen. Now, how does oxygen float around? As you guys know from Clone-Faber-Ha, it floats around as O2, right? And it's a gas. And that, of course, is going to form sodium carbonate. And I get an enthalpy value of a negative 1131 kilojoules. I'm running out of space there. Wow, that's a lot of energy. So making sodium carbonate is really a favorable thing. It gives off a lot of energy, right? Is it balanced? Well, let's see. 2 NAs. I better put a 2 there, right? One carbon, that's good. But, ooh, there we go with that 3 O's and 2 O's. So we're going to have to use that fraction thing again, right? So I'm going to need 3/2 of an O2. So there you go. What do you think? Is that what you got? Hope so. We're going to practice it later. All right, so let me show you next how useful this can be, because the heat formations are often in a table in your book, and we can use them to find the heat of a reaction for other equations. So let's look at one. All right, here's a reaction. Now, I titled this as Hess's Law Shortcut, and I don't know if anybody would necessarily appreciate that or not. At the higher level, you know, the colleges, they might go, what are you doing? But the nice thing about Hess's law, remember, is all this stuff, it's, you know, enthalpy is a state function. It doesn't matter how we get to this point, whatever value we get here, it just matters that we get there, right? Because think about it. If I said find the enthalpy for this reaction, you'd go, well, hey, give me all those different reactions. I'll add them and flip them and multiply them and do whatever to get this, right? And I'm going to say, well, no, you don't have that information. And then you might go, well, how about giving me some heat values? We'll do some calorimetry. I'll put some stuff in some water and maybe heat it up and find out what the energy changes. And I would say, no, you don't get that. So what could you do? Well, it turns out that if I look up on a table for the heats of formation for these elements right here, pardon me, not these elements, these compounds, I can still do a Hess's law problem, so to speak. Okay? And the way it works is that if I take the products, the heat of formation of these products, because they're produced, right? The heat of formation, they're produced, and I subtract them from the heat of formation of the reactants, I can get the delta H. And technically, it's the delta H of the reaction. All right? I can still find the energy involved in this equation. Isn't that an amazing thing? That's one nice thing about enthalpy being a state function. You can just, whatever way you got to do it, find some heat. All right? So let's look at this. So I'm just gonna write down the numbers that I got from a table that I looked these up. So just a second. All right, so I've put these numbers in. You can see that for this thing right here, pentane, it's 145.7 kilojoules per mole. Notice this one, oxygen, 0. Think about this. Is there any kind of value for the heat of formation for an element? There isn't, okay? So there's no delta H value for any elements. Okay. Then we've got a negative 393.5 for CO2 and 285.8. Now I want to highlight this one thing. Notice it says per mole, right? So it turns out that we've got to really pay attention to these coefficients. So yeah, this is just 1 mole of stuff, but right here, what do I've got? I've got 5 moles of stuff. So I've got to multiply that number by 5, and I've got to multiply this number by 6 to get this to all work out. So the way I do it, I'm going to take the sum. This, by the way, guys, is a sign that says the sum. So it's the sum of the heat of formation of the products. So let's write that out. So if I do that, I'm going to go, going to put a big bracket there. I'm going to go 5 times a negative 393.5 kJ, right? Plus 6 times a negative 2858.58 kilojoules. Now I'm leaving off the mole thing there, but remember, here's a mole. Isn't this just 6 moles? And if this is kilojoules per mole, they cancel out, right? So that's why we're going to just get some kilojoules when we're done there. Okay, so I've got that. So that is the sum of the heat of formation of the products. Now I'm going to subtract that. And really we're subtracting it to make sure the sign works out, because remember, these are heats of formation. So it's almost like the opposite of the formation of this. In fact, if we were to look up the decomposition of it, you'd get a reverse number and all that kind of stuff. But anyways, I'm rambling. Let's just write these out. Minus a negative 145.7 kilojoules, plus, of course, 0. So there we go. Now, I work those out. On one side, I get, when I multiply those two numbers and add them together, I get a negative 3,682.3 kilojoules. Check my math for me. Minus, and really, what am I doing? Look at this. I'm adding, right? I'm adding that number, so it's really plus 145.7. Oops, I don't know why these points disappear sometimes. All right, so when I work that out, I get the heat of this reaction is 3,536.6 kilojoules. And there you have it. Now, it's kilojoules per mole of this thing, right? But if you really wanted to work it out, it's per 5 moles of CO2 or per 6 moles of H2O, because it's the heat of the entire reaction. So there we have it. A little Hess's law sort of shortcut. There's all sorts of things you could do with energy. And if you have any questions, we'll talk about this in class. Hope this made sense to you. See you next time.